Great. So tonight's speaker is someone I know well because we spend our Saturday afternoons guiding people around the AWA's museum, the Communication History Museum. By the way, who in here has never been to the museum? Fair number of you. 1 o'clock Saturday afternoon. If you're not doing anything, come down and either Dave or I will be happy to show you around, or you can wander around by yourself. It really is a good way of spending a couple of hours, especially in the sort of weather we're having now and you don't want to be outside. All right, so Dave is a real electronics engineer, so he knows what he's talking about, whereas people like I just make it up. He is a member of SIARC, the Canandaigua Club, and he has given this presentation there. So presumably it got a good enough reception that he believes we would like it. I'm sure it's going to be very interesting. Dave is not currently a member of RARA. What he doesn't realize is at the end of this, he will be, because we make our speakers an honorary member for the year if they're not already members. So over to you, Dave.
Okay, thank you. Yes, thank you for a good introduction. So I'm just going to go right in here. Yeah. All right. So obviously, knowing your frequency has been very important throughout the years. Participating in NETs, SCEDs, FRC, FCC regulations. We don't want any pink tickets in our world. So it's a lot easier to measure frequencies now than it used to be. In the beginning, if you look back in the early days of radio, everything was wavelengths. And we still have some semblance of that today with our 80, 40, 160 meter bands. It was wavelengths because it was easier to measure. If you think in the 1910s, 1920s, it was related to the antenna length. With a wave meter, you could get an approximate idea of your frequency. So this is the math slide, real complicated math. C is lambda F, and we use 300 times 10 to the 6 meters per second because we're radio people. The physics people will do a much more detailed number. So some common frequencies and wavelengths. And I'm sure most of you, all of you, knows the relationship. All right, so in the beginning, they measured wavelength with lecture wires. And you can do this now, depending on how much wire you want to put out. But there were long parallel wires, and they need to be a multiple of wavelength because you're looking for the nulls or the peaks. This I got out of Hackaday, and this was for a fairly high, several hundred megahertz test. And you just inductively coupled the RF to the wires, and you're looking for nulls. Oftentimes they'll use like a neon bulb or a meter with a peak detector. So you look for peaks or nulls and determine the wavelength of your RF signal. And I was reading about, they actually did this back in the 20s for like broadcast stations. And so you can imagine an AM broadcaster and how much wire they had to put out to measure the wavelength. So obviously this was not a real practical way of keeping track of frequency for your average ham. So they came up with wave meters. And so I brought in my wave meter. Actually, I have two. This is from the 20s, and here's your tuned capacitor, your calibrated capacitor, and the appropriate coil would plug in. And then you'd look for, on a transmitter, you'd look for a dip or a peak on the plate current, or on the receiver regen, you'd look for a little kick. And then you'd look up on your chart. Now this chart is for my other wave meter. So I bought a 358 wave meter, and it's the general purpose one that would be used for engineering. But I didn't know much about them, and so I got it, and then after I researched, I realized it came with amateur radio coils. So of course, naturally, being a ham radio operator, I have to buy another one, which has the right set. And so I've got the coils, but this is a 558, which was built for hams. The main difference is the general purpose one had a light bulb for checking transmitter coupling, where this would rely on the meters of your radio or the audio for the receiver. And it works a lot like the grid dip meter, same principle of resonance. And then this is the World War II radar wave meter for the 2400 megahertz band. And so it was the same problem of getting accurate. What's neat about this is it uses a micrometer, an actual micrometer, and adjusts a cavity to set the wavelength. But it's got a meter. You look for the peak of the meter, and and then on the bottom, I'll take it out later. On the bottom, there's a chart which tells you what your micrometer setting is versus your frequency. And the general radio wave meter is you look up based on your coil settings. And I'm sure some poor technician was measuring every one of these in the factory and made a chart for each one. So you just have to interpolate for the frequency. So there's basically what I was talking about is it works similar to a dip meter. You get fairly close to your transmitter coils or your receiver coils and look for a response. Just recently, out of total coincidence, the YouTube channel Microwave One with Mike Murphy, he built a hand wave meter and he demonstrates how it works on his channel. So to help out with the amateurs, they started in the 20s to do precision references on the air. So you could zero beat your receiver. And then once you zero beat your receiver, then you can verify your transmitter against your receiver. And so this is an eye chart, but just kind of a few I found. There was a station called W9XL, which set itself up as it was a broadcast station and a standard frequency station all in the same complex. WWV started in the late 20s, and there were also some hams that would have standard frequencies, and there'd be a schedule on when they would transmit, and you could calibrate your receivers with that. Then in the 1930s, crystal references started, and they become much more popular as they got cheaper. And so zero beating with a crystal reference. In fact, this is one I made many, many years ago. It's an 800. It's like an 800 kilohertz microprocessor crystal oscillator and a divider, a little CMOS divider to make a lot of harmonics, and just different taps. So it does 25 kilohertz, 50, or 100. And so it was for a band edge kind of measurement. A lot like the crystal frequency, because a lot of the radios in the 50s had the crystal reference inside. And probably really up until the 80s when they started synthesizing. So, and broadcast stations started using crystals because they became available. So that was certain broadcasters. If you looked in the old Radio News magazine in the 30s, you could see which broadcasters had certified frequencies, so you can tune adjust your broadcast receiver. Didn't really help ham radio a whole lot, unless you had a general coverage receiver. And then World War II, that led to the heterodyne frequency meter. There are lots of different models, but the one that everybody knows about is the BC221. These were everywhere, and they were very, very readily available in surplus. And so it's basically a calibrated oscillator and a mixer. And if you ever want to get a BC221, they're around since they made thousands. You want to make sure you get the one that has the chart for your meter, because they're all calibrated individually. And in fact, there's an interesting article about Philco. Philco came out with an automated system using adding machines and calibrated motors and all sorts of things to be able to make a calibration table book for each meter, because they calibrated each one individually, and it was like 16 hours to do one manually, and the Philco system brought it down to 4 hours, which still seems like a lot, but if you're the one doing the calibration, 4 is better than 16. And to use it, you can couple your signal from your transmitter to the antenna inputs loosely. You don't want to hook this up directly. And then you monitor with the headphones. I found some official HS30 headphones that the book calls out. And you turn to 0 beat with this. So this acts as the receiver. And then you find from your dial settings, and you can get to a couple hertz resolution with this. Pretty accurate. This one needs some retweaking, but it does still work. And for receive, since this is a signal generator, you can do the opposite. Is you can couple this output in your receiver and figure out what your receiver is tuned to. So it works the same way. And so it's very versatile, and they're military World War II, so they're built forever. And this one had a power supply in the back that was a little too homebrew for my liking, so I put a different power supply in it. The original ones ran off of batteries, so you usually see them in wooden boxes or metal boxes. This is the wooden box version on the screen. All right, so in the 50s, frequency counters started. And I didn't realize that it was that early. I thought it was 60s or 70s, but here's an HP 524 from the late 50s. Now, your average ham radio operator probably didn't have an HP 524, because I'm guessing since it was HP in late 50s, it was pricey. But if you owned Collins gear, you could probably afford it. So as digital circuitry started coming around, it's gotten far more, and so now frequency counters are very available. So I have my HP frequency counter I got in Dayton one year. This was basically it was a little Amazon or eBay kit, and it was put in a plastic box, and so this does 1 to 500 megahertz, and it's pretty easy to use. So frequency counters come from all. If you want a free one, there's one in the free pile I saw from the 70s. So these days, most everybody uses frequency counters because, first of all, there's no charts involved, no math. You couple to it. And of course, it depends on how accurate you want to be and how accurate references. For most ham radio use, crystal oscillators are fine. But if you want to do the ARRL frequency measurement test and get to tenths of hertz, you can go with better references. So to use a frequency counter, you want to couple your transmitter, and you either do something like this, where this is a tap, and it's basically a small capacitor that taps off the RF, so you don't get a whole lot of RF. Or I really like this thing because it's got a 30 dB tap. So it's a dummy load with a tap on it. Or the through attenuator, just to save your frequency counter, because know what your limits of your frequency counter input is. I got a frequency counter once because my friend put 100 watts into it, and it needed some repair. And it did need some repair. The whole front end needed to be replaced, but it was, quote, free. So yeah, and you transmit the single carrier. You don't want to be modulated because it drives the counter crazy. So you want to be unmodulated. CW is always best. But yes, the warning there, don't connect your transmitter directly to your counter or you'll have to buy another counter. And there's some websites. And these are some neat articles. And we'll go to questions, but I'll leave the website page up. Yes. I think it's once a year. I did it this year for the first time. It's usually November. And but they're very fast on putting your results in, because it was on a Thursday and Sunday night. It's like, oh, I should enter that in. And they said, oh, results are already in. But what I did, just because to be a little crazy, I got my BC221 going, and I'd zero beat their signal with that, and then measure it with the frequency counter. And with that scheme, my best was 32 hertz, so not too bad. But I knew I wasn't going to compete with the people with the GPS discipline oscillators and the other super sound cards and everything else. So I wanted to go old school. You can get gigahertz counters now. Yeah, yeah. Yeah, you can down convert if you've got a known reference. You can down convert the frequency. It's a lot like how the VHF, UHF microwave guys test, is they'll go right to a lower frequency quickly.
I have three Hewlett-Packard frequency counters, which are a cylinder, silver-plated cylinder with a piston, and you rotate a knob at the top, and it slowly drops the piston, and then you can read the frequency directly. What actually happens is you put the signal in, and then you put it to something like an oscilloscope or an RF meter that can indicate it, and you'll see a tiny, and it's really quite small, it's about a half a decibel drop when you're at resonance, because the cylinder is absorbing the signal. But it's kind of fun. And those operate, obviously, the higher the frequency, the smaller they are. So a 3 gigahertz one is a nice little ornament to put on your shelf, basically.
It's kind of interesting looking at that HP frequency counter. If you look at the YouTube, you'll find, I don't know, I think it's HP. Each one of those digits, they made actually individual digits with vacuum tubes to do the BCD counting, which is really cool. So they're like little modules back in there, they're like cards. That's really neat.
Oh, that was the first one.
Yes, the vertical neon ones. Yes, I have seen those. Yeah, there's a picture I could find. So, but it's yeah, they've been doing it for a long time. And yeah, if you don't have a frequency counter, just invest in. And this old gear from the late 70s, early 80s is very reasonably priced and still very accurate.
You mentioned you have examples of both capacitor coupled and presumably some sort of resistor, either tapping off into a dummy load. Can you comment on the use cases for each? Why one over the other? Is it specific to the counter that you're using? Is there, if you're just have some old equipment at home and need to tap a device somewhere, can you just grab any capacitor out of your parts bin?
Yeah, this is, I think it's like 100 picofarad. And so at HF, it's a fairly large impedance. And that's really what the goal is to make sure that you're just dropping enough of the signal. This one here, it's 30 dB. So this is pretty safe for most anything. And this one, I forget what this beast is. This is a 30 dB attenuator, but this can handle 50 watts. But this is much older. This can handle 100 watts. So just, depends on time. But yeah, you can make your own even resistive tap because frequency counters tend to be a high impedance. So you don't necessarily have to have 50 ohms. The other thing you can do is, like, if you've got an oscilloscope probe, use that in front of your frequency counter, and that'll drop it quite a bit. You'll find, you talk about drift on frequency counters. It all depends on what your frequency counter is using for reference. Like this, this cheap eBay one is using a microprocessor crystal, so it's going to have terrible temperature drift. This uses, I believe, an oven-controlled oscillator, which gives it very much better stability. And if you're really hardcore, you can put an external oscillator in. So if you wanted to get this even more accurate, you could put a GPS disciplined oscillator as its reference. GPS disciplined oscillator accuracy, I think it's a billionth of a hertz. They're pretty darn good. Yeah. Yeah. I mean, check your spec. But I got one from, there's a company in England that makes them for, I think it was $150 or something. It was pretty reasonable for a high amount of accuracy. Okay, discipline oscillators and Doppler effect. Well, what it is, it's using the GPS. To do GPS with any amount of accuracy, you need a very accurate oscillator. So it turns out GPS are little precision oscillators in the sky, GPS satellites. And so what the discipline oscillator does is it takes, typically, it's a TCXO, temperature compensated crystal oscillator, or an oven controlled crystal oscillator, OCXO. Those are the two most common you find around these days. Usually it's a TCXO, and what it'll do is it'll use the GPS signal. GPS receiver will put out a 1 pulse per second or other frequencies. Some will do a kilohertz, some will do a megahertz. It depends on the GPS module you buy. And that is compared to the TCXO. It's technically a voltage controlled temperature compensated crystal oscillator, VCTCXO. I can say that really fast. And that error between the GPS signal and your oscillator signal will cause a correction. And it'll correct the oscillator back on to match. It's basically a very fancy phase lock loop to keep the crystal oscillator and your GPS reference together. Yes. That's all right. It happens to me a lot. Right. Yes. Right. Right. It's just doing a comparison. So a GPS discipline oscillator, typically they'll put a 10 megahertz output like WWV does. And that then goes into your frequency counter. So all it's providing is a very accurate 10 megahertz. And then the frequency counter is what it fundamentally does is it generates a gate signal. So let's say simplistic, for 1 second, it takes your signal and counts the edges of your signal in 1 second. And then from that, it knows the frequency. And that's what this is doing. It's got different selections for how fast the gate is of 0.11 in 10 seconds. And that sets your resolution. So the GPS oscillator is just giving you a very accurate 10 megahertz, which you can then determine is a 1 second or half a second or a tenth of a second, whatever you need for your frequency counter. Right. Right, because frequency and time are the inverse of each other. So that's the comparison. So you're looking at, we care about frequency in amateur radio, and so we're looking at the frequency. And how a frequency counter works is by measuring the number of transitions during a certain period of time.
So let's say you're adding one of these GPS sources onto your 9700. Exactly what does that do to stabilize the frequency when you're up on like 1 and 2 gigs? So is it multiplying that, or is it using it as part of the phase lock loop circuit? How does that exactly work?
Yeah, basically it's the reference for your phase lock loop. So all the rigs today, I'm going to say a bold statement, all the rigs today are synthesized if they've got fancy dials and displays and things like that. So that reference inside your radio is a 10 megahertz reference. And so what you're doing with the external reference is replacing the internal one with a better one. So you know exactly where the band edge is rather than close to. Right. Right. So if you like operating right at the band edge. Yes. Modern radios, most of them these days are probably using 1 part per million or better oscillators. And so the math is pretty easy. So if you're at 28 megahertz, 1 parts per million is 28 hertz. So that's your actually. I think a lot of them are better than that now, but a 1 part per million is pretty good way to go. And you'll see some of the high-end ones like the ASUs and the ICOMs. You can get the very accurate oscillator as an option.
So you mentioned previously the both age, older equipment being potentially a little bit harder to get accuracy, but also then in the more modern, you have an older HP counter and then your little plastic box LED counter and said, well, it has a crystal in it, but probably not very good. Can you make a comment about, for general amateur radio use, right? In the 70 centimeter and lower bands, when you want to do, I don't know, any testing, checking, adjusting, whatever, is the little black box, even though it's potentially wildly inaccurate, how wildly inaccurate is wild? Or is it sufficient for most things?
It's sufficient for most things, yeah. So we're looking at, this is probably 1 part per million. I don't know the exact specs, but it's probably around 1 part per million. This might be 25 parts per million. And that's over temperature. So in reality, sitting here in room temperature, it's probably within 5 parts per million. So you're not that far off. And if you're not going to, So if you think of, okay, 5 hertz per million, then I won't go that close to the band edge, and you're good. So yeah, just as technology has gotten better, our quest to be more accurate in our radios has gotten better. Where, 100 years ago, 100 hertz was great.
Yeah, my question was specifically within the context of doing repairs. My signal generators don't have any display. They have
Right.
dials, so I need to check them somehow.
Right.
I happen to have an oscilloscope with an accurate frequency counter, but when I forget to replace the caps in it and they inevitably destroy the power supply, I'm thinking about my alternatives.
Yeah. No, these real off-the-shelf ones, really inexpensive, and for everyday use, they're fine. I mean, if you just want to check how far off your handheld is or something like, this will do just as good a job as you need. So it just depends on how super accurate you need to be. And well, it's like anything else with precision. It depends on how obsessive you want to get. Frequency measurement test guys are far more obsessive than I am.
Good evening, everyone. And Brad, KE2CZU. And so I believe last year, my first meeting, they were doing FT8, which was digital, which was for my first meeting, what the hell has this got to do with radio? So now, 1 year later, we're working with World War II test equipment. What in the hell does that got to do with radio? I just bought a brand new ICOM 7300, the year 2024. Do I need one of these boxes to figure out what the signal is? And if it's not to 1/1000th of a whatever, is it still going to work? That's all I got.
Okay, that's a good question. Your 7300 probably outclasses most everything on the table here. Well, you can always do what they did 100 years ago, tune to WWV at 10 megahertz or 5 megahertz and see how close you are. And I just did that with I've got Yaesu FTDX10, which is similar to the 7300. My dad's got a 7300. And found it was pretty rock solid, so I'm happy. So yeah, that's the fundamental thing. If you've got an HF receiver, tune it to WWV and see what your frequency is.
One of the better ones to look at for trying to do receivers and so on is a component called a step recovery diode. And what that's used for is if you want to generate harmonics. So if you take a signal at whatever the frequency is, a standard frequency, and you put it through a step recovery diode, you can get harmonics that are out to in some cases out to the 100th harmonic. And then when you're doing that, take some of those, and if you get them divided down and use lower frequencies, you can get this comb. And so the comb between the two signals is something that's you can get down to kilohertz and so on. And so you can pick one of those if your receiver is very good to where it goes. Just turn it off and use 1 megahertz to start, 100 kilohertz. Add that in, 10 kilohertz, 1 kilo. As you go down, you're getting closer and closer, and so you can get that without ever really trying, but using harmonics.
Yes, and that's similar to what this does, is it just generates using CMOS logic, generates harmonics through the HF range. Yes.
Somewhere in my stash of goodies, I'm sure I have a Heathkit 100 kilohertz crystal voice. Can you talk a little bit about how that's used? Because I've always been puzzled as to if it's really 101 kilohertz, and I'm looking at my 4 meg signal. Am I on the 40th or the 41st or the 39th harmonic. I never really could figure out how to tell.
Yeah, basically what it'll do is it'll put out a signal every 100 kilohertz. And so it'll tell you you're on some multiple of 100 kilohertz. And if you want to know, you can always tune to WWV and turn the calibrator on and make sure that you're zero beating, so your calibrator hasn't drifted over all the years. But yeah, basically what it is, if you turn a 100 kilohertz signal on, like that one, as you tune across at every 100 kilohertz increment, you'll hear a tone. And so that was the idea with the 100 kilohertz calibrators, is since the ham radio band edges are multiples of 100 kilohertz, you can tell where they are roughly.
So there's a little trimmer cap to load the crystal and vary it a little bit, and trying to again figure out how to make sure that I'm on 100 kilohertz and not some other odd multiple that by the time I get to WWV at 5 meg, that I'm again not at the 49th or 51st.
Yeah. No, the easy solution is just get a good counter and measure your 100 kilohertz. That's why I do, because I have a counter. But yeah, the other is go to 10 megahertz or 5 megahertz and see if when you turn the calibrator on, do you hear a tone or is it zero beating? And then adjusting. And if you've got a modern like the 7300 where you've got the nice spectrum display, you can take your that's what I did for the frequency measurement test. I took the transmitted signal, and then I had the VC210, and I just tune it watching the screen until the two signals were on top of each other. Yeah.
I just wanted to put a finer point on Todd's question to check my understanding of what you've explained here. So this will generate spikes 100 kilohertz apart, and there's this adjustment that's going to shift all of the spikes upper or lower, but not change the distance between them. Something fundamental to the circuit is ensuring that they're always 100 kilohertz apart.
Well, they'll vary a little bit. So if it's 101 kilohertz, then they're going to be every 101 kilohertz apart.
Okay.
So it's a multiplier.
So it is actually potentially quite a challenge to be sure that you're right.
Yes.
Yeah.
Yeah. One of the benefits is crystals don't drift that far away. It's unlikely you're going to have something that drifts, 400 parts per million in a crystal. If your crystal's that far off, there's something horribly wrong somewhere. Because yeah, just an ordinary microprocessor crystal that you'd get at a Hamfest is probably 25 to 50 parts per million. And that's spec'd over temperature and everything. So it's at room temperature, it's much more accurate than that. So 50-year-old Heathkit crystal is probably a few hertz off, but it's not going to be tens of hertz off. It's a slab of quartz. So it's an earth element. And yes. In fact, there's a really neat, where did I see it? I forget the name on YouTube. There's a really neat video from the 40s on how they made crystal oscillators. I think it goes through, I believe it's Marie Curie who discovered the piezoelectric effect, where certain materials will vibrate under an electric field and vice versa, create an electric field from vibration. Like your sparkers for gas grills is doing something similar. It's squeezing a crystal, and when it lets go, electric charge comes out. Right. The crystals, well, basically it's when the phase lock loop became cheap, which was the 80s. They had phase lock loops in the 60s, but they were expensive. Yeah, so everything was VFOs and crystal oscillators through the 70s. And then in the 80s, they started doing synthesizers with phase lock loops. And what that basically is doing is you're taking a single crystal reference and multiplying that through circuitry, the frequency synthesizer, to make the different frequencies. And so it's always been kind of crystal based. And if you think about some of the older QRP rigs, some you can see on around today, where you're taking a crystal and then you're using a trimmer cap to slightly adjust the crystal frequency. Right, vintage radio. Yeah, there's a few out there using vintage radios. The cool thing about HF ham radio is you can still use a radio from 50 years ago or more, and it'll still work. Unfortunately, if you're doing VHF, you're kind of limited because old VHF was AM and new VHF is FM. So you're really not doing anything from anything older than the 70s in VHF. Yes, back in the 70s, I forget when the rule changed. I think it was like 73 or something like that. All novices had to work on crystals. And in fact, it was a different era. It was before my time. But apparently, you only had a handful of crystals, and other people only had a handful of crystals. So people were used to operating split. So I've very rarely ever operated split these days, because everybody can tune to my frequency, I can tune to theirs. But in the old novice band with crystals, is you would be on your crystal, and then you're listening to somebody else on their crystal, and it was a different world.
I'm sorry I keep interrupting, but I go back, way back. And so one of the things that's kind of interesting with crystals is some of the World War II crystals, I guess it was the FT crystals that you could take apart and take the little crystal out. Well, a crystal, in order to change its frequency, you can do that by loading the circuit that it's in, or you can take it and put mass. A crystal is actually a micro scale. The mass that's on the crystal determines its operating frequency. So if you see crystals now, it's all plated. Well, if you want to take that and change the frequency, get an S or like silver nitrate, where you can do electrode depositing or take it away. Either take it or add it, and that's one way you can change the frequency. Or back in the days that I remember, you took a lead pencil and you would just put a little mark on the crystal, and that would reduce the frequency. It would always go down. So you could always take that. So some of the old days, those are the tricks that you had to use.
Yes, and it was always easier to go up in frequency on a crystal than down. More mass, but shaving them down to go up in frequency. Yes. Yeah, now they use. Yes.
It's amazing how much World War II pushed all this stuff forward.
And just a little side note, World War II crystal was such a big deal, and natural quartz was so. They actually stationed people in South America to guard the crystal mines. And then the other thing is, they were so worried about crystals that to protect them from being bombed, they moved the crystal manufacturers to Kansas City, the dead center of the country.
So I just wanted to, because we've talked about a few things related to crystals and videos, I wanted to tell people that 1943 video is called From Raw Crystal to Crystal Oscillator. Crystals Go to War in 1943, and you can find it on the AWA Museum YouTube listing. And it was fresh in my head because for some reason I watched it yesterday.
Yes, it's. Yeah.
And also in terms of modifying crystals. On Hackaday, Andy Flowers, who was presented here before, K0SM, has a post on Hackaday about pulling a crystal by grinding it, because Andy does a lot of really, really old style radio work and publishes some of it. So that's also out there if you want to see someone today taking some old crystal and physically modifying it to adjust its frequency property.
I had a question about how do you zero beat an AM station? You mentioned zero beating WWV. How do you zero beat an AM station?
Well, it's easier to change your radio to CW, but to do it, you could put it on a very narrow filter, a very narrow audio filter, and you can peak it. I mean, it's not as good as zero beating with the CW, but yeah, if you narrow up your bandwidth. Yes, that's the other way of doing it. Yeah, with your BFO and basically putting it in the CW mode.
Actually, if you excuse me, if you do it right, when you do your zero beat, when you get down below the bandwidth of the audio, whatever the audio is in the receiver, you're going to lose it, but you keep listening and listen for the noise, because the noise is going to tell you when you actually get to zero.
Yep. Or you do both sides and then find the average.
You mentioned that the calibrated chart for your 221 was, kind of a big deal to automate that. I'm curious, after what, 75, 80 years, how stable is it, and is that chart any relevant, or if you had any old chart, it would be just about as good?
Well, that's a good question. All right, so I'm going to talk about mine because that's the one I've studied. Accuracy. This is after sitting for warming up. It was very stable, but it is off frequency, and there are trimmers in here. There's a trimmer for the crystal. There's a crystal reference that you zero beat because you can. There's a correction knob, so you can bring your crystal, because there are crystal checkpoints in the manual. So you set your crystal checkpoint, turn the crystal on, and zero beat that, and then that page of the chart is accurate. But there's two trimmers on the side and one in the front, and being around 80 years old, they're all seized, and I need to take the whole thing apart and clean them, so that, because I've tried moving them and I'm really afraid of breaking them with my screwdriver, so I have to take apart and get rid of the corrosion, then readjust it back to where it was. And so basically what I'm going to do is get the crystal points back where they used to be, and because I don't want to make my own chart. But yes, if you find one in the wild, it doesn't have a chart, you can make your own chart with a frequency counter and a lot of patience. But yeah, it'd be the 16-hour chart if you're doing it by hand. Yes.
So I'm just curious, because I heard you mentioned earlier that people are into using vintage radio equipment, and you obviously have some vintage radio equipment that you're interested in. I worked at the Eastman Museum for about a decade, and I taught photo workshops, so I know a lot of people who like to use vintage equipment and use vintage processes. And in some cases with photography, you do gain something that you don't get from a digital camera or a modern camera system. So versus using a new modern radio versus vintage radio, do you get something different, or is it more just about like, yeah, I can still do that?
Oh, that's an excellent question. There are some things that are, I would say probably AM is a big deal. Back in, like for broadcast receivers, an AM broadcast receiver from 1930 is probably going to sound better than an AM radio receiver you buy today, because they put more time into making it good, or AM is an afterthought. So I think a lot of the vintage gear has much better transmit AM capability. You do kind of hear that on the air. It's a little more full and robust where AM. And the other thing is some of the vintage gear, being tubes, will have more power. Like I'm restoring a Viking Valiant, and it can do 150 watts CW and 125 watts AM, I think, where my little Yaesu can only do 25 watts AM. So there's some differences there. And then some of it is just the sport of, you know, doing it the old-fashioned way is a little more challenging. And so similar to photography, you can certainly go take a picture and upload it, but to develop it and do all the, you know, there's some of that. The AWA, shameless plug, has a few on-air events featuring different levels of vintage equipment, all the way to 1929. So there's a 1929 event where people are only using tubes that were available in 1929 or earlier. They have an AM event. They have, I think one event is everything before 1950, before 1970, before 1930. They tend to be different. And there's some other vintage radio nets where people have, you know, pick your favorite old radio. There's probably a net out there for it. Oh, yeah, if you say 1975, I'm sure there's a great debate, but I think most everyone would say Collins. Big. Yeah. Collins equipment was always expensive. I don't know about 1975 prices. We have a KW1 transmitter at the AWA Museum. It's a 1,000-watt Collins transmitter. In 1953, it was $3,850. And if you do it effectively times 10 to today's money, it'd be a $38,000 transmitter.
So we're talking the price of an automobile or a radio.
Right, a really nice automobile or a transmitter. It doesn't even receive. It's just a transmitter. The receiver is extra.
Do we have any other questions? I wanted to just make a couple of comments in regard to the question about vintage equipment. I'd say another benefit is if you're not working with digital electronics every day, you're going to find working on 1970s, 1980s gear a lot easier than trying to fix your latest Yaesu radio. I certainly wouldn't try to fix my modern rig. So do we have any more questions? Right, well, I'd like to thank Dave. I thought that was really interesting. Totally enjoyed it. And I do have a question for you, Dave. Sorry to put you on the spot, but did you get your radio working for SAQ and did you hear it at the weekend?
Here we are. We on? Okay. So, for those that don't know, SAQ is an Alexanderson alternator in Sweden. It's the last one that's working, I believe. And it's this massive thing. I mean, it's a motor generator on a huge scale. It generates like a couple kilowatts. Now, here's the fun part. It's 17.2 kilohertz. Yes, kilohertz. And so I looked around. I don't have a radio to receive it. And this past weekend, for the 100th anniversary, 100 years ago, SAQ came on the air, and they were doing they had a YouTube video which I watched, and they were transmitting a message at 1100 UTC, and you can do the math on that. But it was early in the morning Sunday. And so I made a little up converter that I found that converts 17.2 into the 30 meter band, adds 10 megahertz. And that worked. I was listening to WWVB. And I was getting to 60 kilohertz, great. And so then I'm there early Sunday morning, way earlier than I usually am. And I'm listening and I'm watching the YouTube and they're transmitting and I'm hearing nothing. And there was a chat, and basically if you were in Europe, you could pick up the signal, but no one over here seemed to get it. So Mike Murphy, who does the microwave 1 channel, he was on. He wasn't hearing it in New Hampshire, and he's got a bigger antenna than I was using, and so it wasn't making it over the pond. And 17.2 kilohertz is, I think I did the math. It's like a 468 divided by the frequency in megahertz. It's like 29,000 feet. So it's a long antenna for a dipole.
Well, you have another chance Christmas
Yes,
Eve.
I'm going to try
remember.
Christmas Eve. Maybe it'll be colder and a little better noise floor.
Well, at least you got up. I woke up half an hour too late, so I didn't try. Thanks again, Dave.
All right, thank you. Thank you all.